All right, so today we're talking about inverse functions, section 5-6. Last section before your test. You guys are going to be able to find the inverse of a function, determine if two functions are inverse. I'm just going to give you like two random functions. You're going to be able to determine if they're inverses of each other. You're going to be able to also graph inverse functions. Just a whole bunch of stuff with inverses. Okay, just a whole bunch of stuff. All right, so we're going to start out with the green foldable that has what is a one-to-one function on it. Okay, that's the first one. What is a one-to-one function? All right. Now, before we talk about one-to-one, does anybody know what makes an equation a function? Before we talk about like a one-to-one function. Yes. Anything else? Anything else? No. Not every equation that you get is going to be a function. Not every equation that you get is a function. You want to be a little more specific. A parabola is an example of a function. Yes, it is something with the vertical line test. How do you know about the vertical line test? Algebra. Yeah, so you've learned this. You've learned this. Okay, thank you. I was waiting for that. Yes, you have learned this. Functions, vertical line test. Anybody remember what that is besides joining? At least once? Only once. Only once. If it's a function, then a vertical line is only going to cross that graph one time. In other words, there's only one input for every output, okay? So that's why I said a quadratic, a parabola, that's an example of a function, because if I draw a vertical line at any point in time on this graph, it only hits it one time, okay? A horizontal line, y equals 3. Is that a function? Yes, it is a function. All right. Is a circle a function? No, clearly it hits it at 2 points. Okay, so now we're good on what's refresh our memory about what's a function. One input for every output? Yes, yes? So a one-to-one function is a function in which every element of the range of the output corresponds with exactly one element of the domain, the input. Okay, so that's pretty much like the reverse. So a function, there's one input for every output. So there's one element in your domain for every element in your range. But a one-to-one function is the opposite. Okay, it is the opposite. Here's a function. This one right here represents the cubic function, y equals x cubed. Okay, if you notice, your range outputs, -8, -1, 0, 1, and 0. Okay, each one of these, every element in the range corresponds to exactly one element in the domain. Okay? However, this one here, this one is not one-to-one. Okay? This is actually so not correct. Does this say 0 on y'all's? It should actually say an 8. Fix it. Make sure it's an 8. I was like, that's still very wrong. All right, so if you change that to an 8, now you see that there's different y values for every type of x value that's there. But if you look here on the quadratic, x squared is not a one-to-one function. Okay, as you can see, 4 is shared with -2 and +2. Another way that can be represented, I don't know if you guys ever learned this in your Algebra 1 days. They were called mapping diagrams. No. Okay, so you have your outputs and you would have your inputs. Pretend like that's an elongated circle. Okay, and then you have arrows that were drawn. You guys never? Oh, wow. Okay, well, this is another way to look at every element. Every element in your range should only correspond to exactly one element in your domain. So in other words, if 0 goes to 0, there should only be one arrow coming from the y bubble to the x bubble. If you look at 1 goes to -1, and it also goes to +1. That should not happen. There should not be 2 arrows coming from the same output value. Okay? Same thing with 4. 4 goes to positive 2 and it goes to negative 2. It should not have two arrows coming from one output value to two different input values. Okay? So you can see it from a table. You can see it from a mapping diagram. You can also see it from a set of points as well. Okay? Because the table is nothing but a set of points just written in the table. All right? Another way to determine if a function is one-to-one is by the opposite of the vertical line test. A vertical line test tells you if you have a function. The horizontal line test tells you if you have a one-to-one function. Okay? If you can draw a horizontal line that intersects the graph at only one location, then your function is one-to-one. That's why your parabola is not one-to-one. Okay? So why are we learning about one-to-one functions now? Well, it pertains to the inverse of a function. Okay? The inverse of a function is the relation formed when the independent variable is exchanged with the dependent variable. In other words, you're exchanging your x and your y for each other. Okay? The process in finding the inverse is simply the switching of x and y, your x and y coordinates. When you graph it, it is a reflection over the line y equals x. So, the inverse of a function, you are switching your x and y coordinates, and it's a reflection over the line y equals x. Y equals x is nothing but a line that has a slope of 1, a y-intercept of 0, 0. And as you can see on the graphs of my original function, let's just call this f of x. 1, 0, 1, 1, 2, 2, 4. If I switch them, I get the coordinates of my inverse function. And that is a perfect reflection over the line y equals x. Okay? If the graph that you draw passes the horizontal line test, if the original graph passes the horizontal line test, that means your inverse is a function. And in order to be a function, it has to pass the what? The vertical line test. So if this is my original function and this is my inverse, it should pass the vertical line test, which it does. So if you're ever asked, is the inverse a function? Look at the original. If it passes the horizontal line test, then you know without graphing, then your inverse is going to be a function. Did everybody catch that? Okay. So I'll write it. If your original function passes the horizontal line test, then your inverse function let me not confuse it. Then the inverse is a function. I'll say that instead. In other words, that graph will pass the vertical line test. Because you will be given a graph and you may be asked, is the inverse a function? Instead of figuring out what the points are on your original function, switching them, and then graphing that, you can know by just doing the horizontal line test. Okay? Yes. The horizontal line test is similar to the vertical line test. It tells you whether or not a function is going to be one-to-one. It should not hit at two different places. Yes?
Is y equals 3 and y equals anything like an interval function?
So any y equals a number, those are all functions, but their inverse is not going to be a function. Okay? So if I have x and y, and I have the equation y equals 3, for example.
Sorry, x equals.
Oh, you want to do the other way? Okay. That does make a difference. All right. If you have x equals 3, first off, is the original function or the original equation a function? No. So if the original is not a function, there's no, then that's not going to, like you just stop there. However, if this is your original equation, y equals 3, is y equals 3 a function? Will its inverse be a function? Because it does not pass the horizontal line test, because that is what it is a horizontal line. And if you think about it, never mind, we haven't gotten there yet. Pull it back. No, pull it back. We're going to get there. Questions?
So that's the function, and then x equals 3 would be a 1-to-1 function?
You wouldn't even consider it because it's not even a function itself. Okay? Like if the first test, which is always is it a function, if that doesn't pass, then you don't even consider the inverse. Other questions? You sure? Let's see it apply. So if a function is 1-to-1, then the inverse is a function. That's what you guys just wrote down. Okay? And it's called the inverse function. And that's the notation, f to the -1 of x. That -1 is in the exponent of f. And the inverse, all it does is it just switches the x and y coordinates. Okay? All it does is switches the x and y coordinates. So, the inverse function, you're just switching your x and y's, literally. So, if you have an x on the original function with its corresponding y, then all you do is flip it and it becomes the x on your inverse and the y on your original, the x on your inverse and the y on your inverse. Same thing, if you have 1, 1, when you flip it, it still is 1, 1, just on your inverse. If it's 2, 3, then it becomes 3, 2 on your inverse. Okay? Now, if a function is not 1-to-1, for example, like the quadratic, then what you have to do is you have to restrict your domain so then that way you can indeed find an inverse function. Okay? So if I restrict x squared to where it's just the x values that are greater than 0, that means I'm starting here and I'm only looking at one side of it. Before, I wouldn't have had an inverse because it didn't pass the horizontal line test. But now, if I take away the whole left side, does it pass the horizontal line test? Yes, it does. So then from there, I can find an inverse function. Okay? So then you just switch 0, 0 still stays 0, 0. 1, 1 still stays 1, 1. But 4, 2 turns into 2, 4. And that's actually backwards. It should be. Fix this, 2, 4, and then 4, 2. Fix that. So far, what are some of the main things that you're seeing that are related to inverse functions? What about it? Flip. Okay. So I got some flipping going on. Anything else? It's okay. Maybe if not now, maybe by the end of all the foldable flaps. Okay. But definitely you're switching your x and y to get your inverse. Proving that functions are indeed inverses of each other. Okay? You got to look at their compositions. We've talked about compositions with operations. Okay? You have two functions, f of x equals 2x plus 6, and the inverse function f to the -1 of x, which we'll just call g of x, equals 1/2 x minus 3. If you're able to find the composite of f of g of x and g of f of x, and they both equal x. I'll say that again. If you do the composite f of g of x And the other way, g of f of x, and they both equal x, then the two functions are inverses. So in problems like this, you're going to be given two functions, and you're going to be asked to determine if they are inverses of each other. You need to do the composite, f of g of x and g of f of x. If after you've simplified, if they both equal x and only x, one positive x, then they are both functions. Then they're inverses of each other, inverse functions. Mm-hmm. But the main thing about inverses is you're just switching your x's and your y's and then doing the composite of the two functions both ways. We're going to look at an example. You already have one written down now in your notes, but I think it's going to be better for you to see it actually worked out. Okay? Let's take this first one. In order to determine if they are inverse of each other, this is nothing in any of your foldables, okay? I just want to make sure that you guys see this worked out. We got f of x, which is 2x plus 3, and we have g of x, which is negative 3x minus 2. I need to do f of g of x as well as g of f of x to determine if these are inverse functions. So remember, we talked about composite functions last week. This means I got to plug g into f, and you want to make sure that here's f, I'm plugging g into this function. Does everybody see that? Some of you guys on your homework, you forgot about that additional part at the end, which I'm going to hand back, by the way. So just make sure that you're careful there. So now I'm going to simplify this. When I distribute, this gives me a negative 6x minus 4 plus 3. When I combine like terms, what do I get? Does that equal x? Because it doesn't equal x, then those two functions are not inverses of each other. And you can stop there. Like it doesn't simplify down to give you x. Like once you do the composite, it should equal x in order for it to be an inverse, in order for them to be inverses. But if it doesn't, like this one doesn't, then they're not inverses of each other. It's literally just x, like the variable x. That's a good question. Let's look at this one, okay? I have to do f of g of x. So again, I'm plugging g into x in f. Everyone see it? So far, so good? Now, when I simplify this, what happens to this 2 on the outside and this 2 at the bottom? They cancel. This gives you x plus 4 minus 4. What is that? X. So far, so good, but you just can't leave it as that. You have to do it the other way. You have to check g of f of x. Because sometimes it could work one way, but not for the other. All right? So now I'm going to do... So there's f into g. It still equals x, right? Because negative 4 plus 4 gives you a 2x over 2, and that gives you x. So since they both equal x's, are these inverses?
Yes.
Yes, they're inverses. And that's how you approve if two functions are inverses of each other. Doing the composite both ways. Questions?
So after we find out the inverses on the homework, we're gonna tell if they're one on one or not.
You'll just have to determine if they are inverses of each other. And the thing is that if they are inverses, then you know automatically the original function f of x was indeed 1-to-1. So like a question like that would be something completely different. Like I'll give you a function or I'll give you a graph and I'll ask you, is it 1-to-1? Or I might give you a set of ordered pairs and I'll ask you if it's 1-to-1. And you'll know a set of ordered pairs is 1-to-1 if every number in the output has one lone number in the input. Yes, because they're inverses. So it's the opposite. Everything's flipped. All right. Where are we at? All right, next foldable. All right. I want you guys to do this example of proving whether these functions are inverses of each other. In order to prove if they're inverses of each other, what does that mean? They have to both equal x when you do f of g of x and g of f of x. So go ahead and do the composite. This one's the easy one. Are they inverses?
Yes.
Yes, they are. When I take g and I plug it into f, it gives me this. What's the square root of x squared?
X.
Just regular x. Okay, so this one works out. When I go the other way, it becomes the square root of x squared. And a square root and a square do what? They cancel out. So yes, these are inverses of each other. Now, did anybody notice this part right up here? What does that mean? Yep. It's only this part right here because I'm only looking at the values that are greater than 0. Otherwise, could that pink parabola pass the horizontal line test? No. And if it doesn't pass the horizontal line test, then it's not going to have an inverse function. Or its inverse is not going to be a function. Questions? That was an easy one, so you have that one in your notes. How to find the inverse function. I might just give you an equation. I might just ask you, what is the inverse? You have to find it. It is 5 steps. Really, it's only kind of 3 once you look at what the steps are. Okay? The first thing, you want to make sure that it's 1-to-1. Because if it's not 1-to-1, then there is no inverse function. So you need to make sure you restrict your domain until it is a 1-to-1 function. In other words, it passes the horizontal line test. After that, you want to replace f of x with y because that's pretty much what f of x equals. It is y. And then once you finally get that correct notation, then that's when you switch x and y. Once you switch x and y, you solve for y. And then replace y with the correct notation to indicate inverse. You do not want to leave the inverse function as y equals, because y would indicate the original function, not the inverse function. So you want to make sure that you use the correct notation. So make sure it's 1-to-1. Trade out f of x with y, switch x and y, solve, and replace. Correct notation. Let's take a look at an example. I think it's 2 examples. Yeah. All right. First one, and we're also going to state the domain. Good time to practice interval notation, which is at the very beginning of this unit. We need to find the inverse of f of x equals 2x plus 4. Then state the domain of the inverse. We're going to state the domain of the inverse. And then we're going to use the graph to support our answer. So, 2x plus 4, what does it look like? Huh? It starts at 4. It goes up 2 over 1, up 2 over 1, or okay? So this is what the original function looks like, f of x. Not my best line, but you guys get my point. Is this a function? Yes, it passes the vertical line test. So because it is a function, I can actually find its inverse. So now it is, and on top of that, does it pass the horizontal line test? So then its inverse is going to be a function. So then I'm good to go. I'm ready to do this. So I need to replace f of x with y. Then I need to switch x and y. Then I need to solve for y. How do I solve for y? How do I get y by itself? Subtract 4. Divide by 2. So that was step 4. Then I replace y with the inverse notation, which is f to the negative 1 of x equals x minus 4 over 2. This can also be written as 1/2 x minus 2. Does everybody see how and why it can be written this way? Divide the x by 2, divide the 4 by 2. Either one will be acceptable. Now, if that's the inverse function, what is its domain? Negative infinity to infinity. Because this is, what does this look like? Just a line, right? A line that has a y-intercept where? -2 and has a slope of up 1 over 2, up 1 over 2, or down 1, left 2. Okay? So yes, all lines' domains are negative infinity to infinity. What if I wanted to write that in set notation? Who remembers? The set of x such that element all real numbers. Good job. Now again, these are not my best lines, but inverse functions are a reflection over what line? Not the origin, but y equals x. So here is, that's a terrible line. There's the top half of y equals x, and then here is the bottom half. Like I said, not my best lines, because technically they should have intersected at that point, but I missed it. But this is a reflection over that line. So if I give you a graph, you should be able to graph my inverse. If you want to, you can just take the points, switch them, and graph them, or you can reflect it over that line. Questions? To the next one. Find the inverse of x squared minus 4. Then state the domain of the inverse, and if you need to, use your graph to support your answer. I'm going to walk around. If you guys have any questions, make sure you let me know. All right. So we have to find the inverse of f of x equals x squared minus 4. I think everyone did okay with finding the inverse, okay? You all, some of you guys went straight into changing f of x to y, switching x and y, and then solving. So you add 4, and then what do you have to do? You take the square root. Now, when you take the square root in an equation, what do you have to remember that a lot of you guys did not remember? Plus or minus. It's going to be plus or minus x plus 4. And then I'm just going to go ahead and change the notation. But wait. Before you change anything, there's something else that some of you guys didn't do until after you graphed it. What does x squared minus 4 look like? It's a parabola that has a y-intercept and a vertex where? 0, -4. And who remembers the pattern? Up 1, 3, 1, 5, 1. What part? No, I'm graphing the original function. Uh-huh. And then, no, -4 represents where the vertex is going to be for this parabola. Abby? The plus or minus is what makes it a parabola after it's been reflected over. You actually only do one of the sides because, remember, quadratics, normally, they look like this. But, does this pass the horizontal line test? No. So it's only going to be what side? The right side. The right side is usually the easier side. So what have we done by only putting the right side? Say again? We restricted the what? The domain. Instead of it being from -infinity to infinity, it was only 0 to infinity. So this was the domain of the original function, which means that my inverse, which a lot of you guys had right, but incorrectly you had it right, it's not going to be plus or minus. It's only going to be what? It's only going to be the positive part because you're only taking the positive part of the quadratic. I'm not done yet, by the way. Yes. Yeah, like you shouldn't even be doing that. Like if there's no inverse, then you shouldn't even be finding the inverse. So that's why it's always kind of good to have an idea of what these graphs look like. So a quadratic, you're going to have to restrict the domain. I would suggest a graph. Yes, you can do this the regular reflection. All right. Yes. This is actually not the domain of the inverse. I'm not done yet. I still got a graph and I still got to find the domain. That's okay. This is the equation. This is the inverse. But I still have to state the domain of my inverse, and on top of that, I'm going to graph it. I'm going to use the graph to show what the domain is. Okay? So, inverse is nothing but switching x and y. So, I can make a table of values to graph the square root of x plus 4. Or I can take these points of this point of 0, negative 4, 1, negative 3, 2, 0, 3, 5. I can take each one of those points and do what with them? Flip them and graph those instead. So instead of it being 0, negative 4, it is negative 4, 0. Instead of it being 1, negative 3, it's going to be negative 3, 1. Instead of it being 2, 0, it's going to be 0, 2. Because remember, the inverse is nothing but switching your x's and your y's. That applies for your graphs. That applies for your table of values. Okay? And the last one, 3, 5 becomes 5, 3. Not my best drawing, but that is what the inverse looks like. And so then the domain of the orange is going to be what? So I could write it in set notation with all the goods. How would I write that in interval notation? Do you guys notice something about that domain? What? True. One side has a bracket, which means it's defined at negative 4, which it was. It was a closed circle there. Infinity always has parentheses. Don't ever forget that. Anything else? No, still the same type of span. It's okay. It's going to come to somebody. The question, do you notice anything about the domain of the inverse? Question. That was my question. Oh, like I knew this was where it was going to start because that's where my original function started. So when I flipped the point of 0, negative 4, I knew that's where my inverse had to start. So it would have been shooting up to the right. I'm trying to hear what the whole thing that you have to say. No. Yeah. I got you this way. Sorry, I guess about me looking at you like, oh. Jesus. I get what you're saying, but it's like if I were to say that everybody understand that, you'd be like, I don't understand it. Okay, give me a second. All right. Anybody can maybe interpret what you just said. Do you remember when we were originally doing interval notation, and I told you that there was 2 different types of restrictions when you were doing it from an equation? Remember, there were 2 restrictions. You couldn't have 0 in the denominator of a fraction, and you couldn't have a negative underneath the radical. So another way you could have done this was going back to that from the very first section of this unit and setting what's underneath the radical greater than or equal to 0 and solving it that way. But that actually wasn't where I was going, but that was actually a good, I think you were trying to get there. Yeah, count your money and come back. So no one else can see it?
Wait, there's something else. Okay.
Yeah, something else. Go ahead.
Oh, okay. So the domain it passes the vertical?
It does, but it's relating to the range of the inverse. Yes? Everybody hear her? The range of the original is the domain of the inverse. So x and y are switched because it's the inverse. Everything's switched. So the domain of the original function is the range of the inverse. And the range of the original function is the domain of the inverse. You see it? And it always applies. It's always like that. Because they're inverse functions. So literally everything is switched. X and Y. Remember, domain is X and range is Y. So those get switched too. Okay? Questions? We're going to practice a little bit. I do want you guys to grab whiteboard markers and felt. Okay, let's look at this example. You're asked to determine if it's not a function, if it is a function but not one-to-one, and if it's a function one-to-one. Okay? So you're labeling A, B, and C as such. Okay? You're labeling A, B, and C as such. For this problem, you have to think, okay? In order for it to not be a function, that means it does not pass the vertical line test. That means that there is multiple outputs for one input, okay? And if you really are struggling, maybe plot the points just on like a little small graph. So then that way you can see, do those points pass the vertical line test? If they pass the vertical line test, then that means yes, it is a function. But if they don't, it's not a function. So, well, no. As long as you do not have the same X for different Y's. So, for example, right here, for this one right here, okay, this one does not work. If I quickly sketch this, right, negative 2, 7, negative 2, 5, 3, 2, 1, 3, 5, 9, okay? Does this pass the vertical line test? No, because of right here, because of those 2 points. If you see, this is the same input but different outputs. So this one is not a function. If it's not a function, then there's no way that it can be one-to-one. It has to be a function in order for it to potentially be one-to-one.
So if the x's are the same, then it's not a function. Okay.
No, it's not a function, which means it can't be one-to-one either. In order for it to be one-to-one, it has to be a function. Let's look at the next one. Let's look at our x's. Do any of our x's repeat? No. So then we know it is a function. Do any of our y's repeat? No. So because none of our x's repeat, none of our y's repeat, that means it's a function and it's one-to-one. Now look at this. Do any of our x's repeat? Do any of our y's repeat? Yes, here. So because our x's don't repeat, that means it is a function, but because our y's repeat, that means it's not one-to-one. So it's a function, but not one-to-one. Question? All right, I want you guys to give this one a try. Give this one a try. Together. All right. So this particular one, okay? I think everyone got to the point where they replaced here. And then you switched. Because you got to remember, you're finding the inverse. So you have to switch your x's and your y's. Now this is where things got a little crazy. You cannot cancel out the y's, or even from the beginning, you can't cancel out the x's because one's being multiplied and one's being subtracted, which means that it's 10 minus x. They're together. You can't do one without the other. So you can't cancel like that. Same thing with 10 and 40. You can't reduce that because it's 10x, 10 times x, and 10 minus x. So you can't reduce that because there's something else happening to the 10 at the bottom. But what you can do, algebra rules, is what? 9 multiplied by 40y. Huh? You can multiply by the denominator to get rid of that denominator. Okay? Wait. So if I multiply, this cancels out over here. So I'm left with 40y on the right-hand side. And what am I left with on the left-hand side? 10x minus yx. Now remember, your goal at this point is to solve for y, which means I need to get y by itself. But what do I see here? There's 2 y's. So shouldn't I potentially get them all on the same side? How do I get this yx over here? Because then I'll be going backwards. Huh? I add yx to both sides. I've already like distributed this over, so there's no, like I've already done the multiplication part to get this.
So when you multiply the 10y,
The 10 minus y.
10 minus y by the top, you get.
They cancel out. That's why you do it. To get rid of the denominator, you multiply both sides by it.
So it just leaves 40y.
Mm-hmm. So now I have 10x equals 40y plus yx. Now that I have them on the same side, can't divide by 10. I'm solving for y. I can't divide by x. That's going to presume. I cannot divide yet. I cannot divide yet. Wait, what you say, AJ? No, I can't combine them because one has a 40 and one has an x, but I could not divide yet. Huh? Can't multiply. You're forgetting all of your rules of anything right now. There is something. Lord have mercy. Okay. I'm trying to solve for y. I have two y's right now. Originally, my y's were on different sides. But by adding over a yx, I now have them both on the same side. And now to get to a point where I just have one y, I need to factor out a y. When I take out a y, what am I left with here? So y times 40 plus x, and now to solve for y, I can what? Divide both sides by 40 plus x. This one right here is probably one of the harder ones that can ever come when you are trying to find the inverse. Okay? But I was hoping that you guys could do this. It might have been too much too soon, but this right here, you switch x and y, and you solve for y by doing your proper algebra rules. Proper algebra rules. Let me hand out your homework, okay? Don't worry, we're going to spend a little bit more time on Thursday working on inverses. So please do your homework.